So talking about limits of integration for our rows, the first thing I want you to do is I want you to get your calculator and I want you to push the mode button, and I want you to choose, instead of function mode, I want you to choose polar mode, and then hit your y equals button at the top there, and you should see r sub 1 equals and r sub 2 equals. And in r sub 1, put our function 2 times the sine of 2 theta. Then I want you to hit your graph button. Now, what you may need to do, because it'll be kind of small, I think, if you just do that, go ahead and go to hit your trace button, and don't do anything, just hit trace, and then hit zoom and choose zoom in, and then hit enter. And I believe when you do all that, you should have something that looks like this on your calculator once you've done all that. And we can see, using our calculator, that we do indeed have a 4-leafed rows. Every different leaf lies in a different quadrant. If we wanted to see, hopefully you can see that little bouncing cursor right there. If we wanted to see the angle measures, hit your trace button. Let's see if this will work here. Hit your trace button. Here we're at the origin, x equals 0, y equals 0, and theta equals 0. Hit your right arrow and you'll see as theta gets bigger, you'll see the little x there, that we're actually tracing out that first leaf in quadrant 1. Since all the leaves of a rows are identical, then basically what we want is the area of one leaf, and then we could multiply that area by 4, and that would give us the area of the entire region. So what we need to do is we need to figure out what our limits of integration are for one leaf. So hopefully you can kind of follow along with that. So let's talk about, let me get rid of some of this mess here and give us some more space. Let's get rid of this. We've already worked with that. Okay, so we know that in quadrant 1, we have a leaf. We know that the leaf begins at theta equals 0. That's going to be our lower limit of integration. So for every one of these, we can just put 0. We know we're going to start integrating at 0. Then we're going to see what theta is here. What is our second theta? What is our upper limit? We'll call this theta L. We'll call this theta sub u. Our lower limit is 0, but if we could find what theta is once we have mapped out or drawn that first leaf in quadrant 1, then all we have to do is come back here and take 4 times that, and we could put a 4 in front of each one of these. 4 times the area of one leaf would give us the area of the whole polar function. So now we've got to determine what is our upper limit. Well, what's true about r right here at the origin? Right here at the pole, r equals 0. Well, we have r. All we have to do is take r and set it equal to 0. So we're 2 times the sine of 2 theta equals 0. We should be able to find all of the theta values, the first, the second, the third, the fourth, the fifth, all those values, where all the angle measures where we're at the pole or where r is 0. So let's solve this for theta. So I'm going to divide both sides by 2. So the sine of 2 theta equals 0, dividing both sides by 2. I'm going to take the sine inverse of both sides. The sine inverse, I'll go ahead and just write it down so we can see this. It'll be in your notes. The sine inverse of the sine of 2 theta on the left is just simply 2 theta. Sine and sine inverse undo each other, right? And so here on the right, I have the sine inverse of 0. So for what angle measures is the sine function equal to 0? Well, let's go back, right, and let's draw our unit circle. Here's 0, it's also 2 pi, and here's pi. And so sine is 0 here, and sine is 0 here. So theta measures definitely of 0 and pi and 2 pi. There are the first three where the sine of 0 equals 0, or where the sine of theta equals 0, I should say. Well, we don't have theta, we have 2 theta. So we're going to set that equal to first 0, then to pi, because remember, we know the lower limit. We want the second time r equals 0. Well, that's going to happen when theta equals pi. So we have 2 theta measures. I'm dividing both sides here by 2. 0 divided by 2 is still 0. That is our lower limit. But our upper limit is pi over 2. So we very easily, by hand, we didn't even really use our calculator, by hand we were able to determine what our upper limit was. So there we go. So now we can just come back here, and we have 4 times, so I'm going to find my antiderivative with respect to theta. The antiderivative of 1 with respect to theta is theta. This is a u substitution now where u is 4 theta. So du is 4 d theta. So I'm off by 1/4, and now we have the integral of the cosine of u du, and so the antiderivative, hopefully you see a lot of repetition in this. So the antiderivative here is 1/4 the sine of 4 theta, and here's the area of the entire region, right? This is just the area from 0 to pi over 2 without the 4 in front, is just the area of this one leaf, but we need the area of all 4 leaves. So, and we're going to do this from 0 to pi over 2. So this is 4, and my upper limit is pi over 2 minus 1/4 the sine. 4 times pi over 2 is 2 pi. So there's my upper limit minus my lower limit, which is 0, minus 1/4. The sine of 4 times 0 is 0. So there we are. So this is 4 times pi over 2. The sine of pi over 2 is 0. This term obviously is 0, and this term is 0. So doing it by hand turns out pretty handy. So the entire area enclosed by this rose in the plane is simply just 2 pi. Right there. So roses are not that difficult. Probably the most difficult part is just determining, is our leaf completely in quadrant 1? Does, the leaf in question, is it going to lie on an axis, or does it lie completely in a quadrant? That's kind of the most tricky part to dealing with roses. Okay, so we have one more example here, and it's one where we're dealing with 2 regions in the plane, 2 polar regions. And so if we want to find the area between 2 curves, or let's say inside one curve but outside the other curve, then this is the formula that we're going to use. And we would say that we might be given big R, which is one function in theta, right, one polar function, and then we might be given little r, which is a separate, unique polar function. So given the fact that we might want to find the area that was inside of big R but outside of little r, or vice versa, then we would use this, and we would pay strict attention. We would draw a picture, and we would pay strict attention whether it was big R minus little r, or little r minus big R. So just like finding the areas between Cartesian curves, establish limits of integration where the curves cross. So we set our equations equal to each other. We're going to solve for the value of theta that makes the equation true, and we want to investigate all of the potential values for theta. All right, so this is just drawing a picture and keeping up with it really well. So let's get started on this. I do think we're going to have one additional video. I don't think we'll get all the way through this example. But this says find the area of the region common to the two regions bounded by the following curves. Let's call this R sub 1 and we'll call this R sub 2. And by the region common, they mean the region that is inside both. Okay, that means it's inside both polar functions. All right, so let's go back here to y equals. I'm going to clear this out. We're going to put, in R1, we're going to put 3 minus 2 sine theta. So 3 minus 2 sine of theta. All right, and now this is a limacon. Notice that. See the minus? This is a limacon. And so now we're in R sub 2. We'll go back here, and in R sub 2 we're going to put 3 minus 2 cosine of theta. So 3 minus 2 cosine of theta. So let's graph this, and we're clearly too big, so let's zoom out. There's one. And there's the other. So we want the region common to both of them. Right here, this region right here, it needs to be inside this limacon and inside this limacon at the same time. So there it is right there. That's what we're looking for. Now, our theta measures that are going to give us that are going to be these intersection points right here. This point and that point where they intersect. And so we could trace, here's R1. See how R1 starts here, and as we move to the right, it goes in the counterclockwise direction. So right there would be the first intersection point, and then we would keep going around until we see the second intersection point, which would be there. We've got to do that by hand. So let's come out of here and let's find our limits of integration. Our limits of integration are going to be when our two limacons intersect. So we're going to have to set them equal to each other and solve for theta. And we're going to need more than one theta value. We're going to need our lower limit and we're going to need our upper limit. All right? And so in this case, when we go back to our formula here, either one of these could be big R or little r because we want to know the values that they have in common. All right? So let's set them equal to each other. 3 minus 2 sine of theta is going to have to equal 3 minus 2 cosine of theta. If I subtract 3 from both sides, that's minus a 3 and minus a 3. That's going to leave me negative 2 sine of theta equals negative 2 cosine of theta. I'm going to divide both sides by negative 2. Just some algebra. Sine of theta equals cosine of theta. So where are sine and cosine equal on the unit circle? Remember, that happens at iterations of pi over 4. It happens at positive pi over 4, where both cosine and sine are positive root 2 over 2, and it happens again at 5 pi over 4. That's where they're both negative root 2 over 2. So there is our lower limit. There's theta L, and here is our upper limit. There's theta sub u. So we can find that by hand really easily. So let's give ourselves some space here. I tell you what, we'll stop here and we'll finish this example on the next video, and that should be the final video for this lesson.